Hey there, welcome back to another video, and in this video we are gonna discuss the cost function of logistic regression. And by function I mean that we are gonna discuss the loss of the logistic regression. So without wasting any more time, let's get into the video. So guys, if you do not know how loss basically is going to affect our program or our output or anything, then I have already explained all of this in my linear regression series, in which I have explained everything from scratch, like how loss is going to affect your thetas or anything like that. So if you haven't watched that video, or if you do not know how loss is going to affect it, then please go and check that video out. Now, in that video we discussed that our loss function is going to generate an error, a graph like this. So this is a convex graph. For that problem it was okay, but when we talk about linear regression, logistic regression, in which our output belongs to 0 to only 1, this our normal error, that was mean squared error, it is not going to generate a graph like this. It is going to generate a graph like this. It can be anything. So there will be basically multiple minima, and what we want to achieve is that we want to achieve this global minima. But using gradient descent, if we get stuck into one of these local minima, then we are not going to be able to get out of that local minima, and our algorithm is going to be stuck. So that's why we cannot use our mean squared error here, because it is a non-convex function in this particular case. And I will explain you more about why it is like this. I have to make another video because it is a little bit complex, but I will make another video like this. So what you have to do here is that we have to choose another loss function or cost. From now on I'm gonna call it cost. So we have to choose another cost function to find the cost of the program. Okay, so for this, what I'm going to use, I am going to choose log likelihood. So, or you can say likelihood of the so basically I'm going to choose the likelihood, and likelihood is a cost function by using which you can find the cost of a algorithm. Okay, so these are the things that we discussed in the last video like this, and you can also represent it like this. Okay, so now if I talk about likelihood, by likelihood I means the probability. Okay, so as you can see here, the probability of y being equal to 1. So what is the probability of y equal to 1, provided that x is given with constraint theta. Okay, so for this, what we are going to use, we are going to use this. Okay, now if you know a little bit about probability, then you will get it very quickly. Now if this is the case for the probability 1, then what is going to be the case uh, when the y is equal to, so what is going to be the probability when y is equal to 0 with x given with constraint as, or with values as theta. So what it is going to do, it is going to be 1 minus this value. And the reason behind that, because total probability is always going to be 1. So let's suppose you are tossing a coin, and if you, the probability of getting a head is let's take 40, although it is always 50-50, but let's suppose it is 40 in this case, then the probability of getting the tail is going to be 60, because it is always 100, or you can say 1. So that's why what I am doing here is I am just doing the minus 1 minus this value, and this is also known as Bernoulli distribution. So you can go and check this out. Now what I'm going to do, I'm going to combine both of them, because right now these two are different. So I'm going to combine both of them, and after combining, what I'm going to get, I'm going to get this result. Okay, so let's suppose let's take how it is going to be the same as this. Okay, so let's take y equal to 1. Okay, so if y is going to be 1, then it is going to be 1, and this value is going to be 1, because 1 minus 1 is 0, and when something has a power of 0, then that value is 1, and this value is same. So what we will get? We will get this output, which is good, and it is correct. Now the next thing that we will get is, let's take y as 0. So this is going to be 0, and this is going to be 0. So now as this has a power of 0, this is going to be 1, and this value is going to be remain same, which is going to be like this. So we have combined both of them. Okay, now we want the optimal theta. So what we need to do is we need to maximize the likelihood. Basically we need to maximize the probability that yes, our output is going to be correct. Okay, so for that what we are going to do, as yeah, so this is our output, or this is our normal probability, and what I am doing here is that I am now getting probability for all the cases. As you can see here, I have attached a I subscript here. So what it is going to do, it is going to get the probability for all other examples, and it is going to multiply them. Okay, now what we can do here is we can just open this and we will get our formula. So this was our formula like this: h theta x I with power y to the I, and this is same, basically this is same as this. We have just added the I subscript. Okay, now you will see that it is going to multiply all of them, so it is going to be a very big number, and if the values are small, then it is going to be a very small number, which is going to be very computationally expensive. Like let's suppose our numbers are like this 0.00001, and now let's suppose it is multiplying these kind of numbers together. So in our computer, for floating points number, we have a precision that we can store, let's say 50 or 60 digits after the decimal point. But if we are going to multiply a lot of these numbers, then we are going to close this value, and it is not going to generate good results. So for this, what I am going to do, I am going to take the log of these values, and what it is going to do, basically log has a property of converting basically multiplication into summation. Okay, so that's why I am taking the log here. So this is going to be a log likelihood. So this what do we say, this cost function is called as log likelihood. Okay, so we are gonna take log on both sides, and after taking the log, what it is going to do, it is going to convert this multiplication into a summation sign, and we can add like this. This is a basically simple log formula. You can search on Google like how log formula works. So this is simple log formula, and you can go with this. Okay, and basically what happened that by using the log formula, it came here and this came here, and they were added together by using that log formula. You have to check that by yourself. So this is going to be our loss for, or you can say this is going to be our cost function for our logistic regression. I hope that it is clear, like why are we using it, the reason behind. Let me just again explain you very simply. When we use MSE for binary classification or for logistic regression, so what happens that it does not create a graph like this, so which is bad, which is very bad, because if it is going to generate a non-convex graph like this, then it can stuck in a local minima like here, and then it is not going to give a very good output. So that's why we are using the log likelihood. What it is going to do is it is going to generate a value like this. So what we can do here, this is the likelihood, or you can say this is the log likelihood. So log likelihood of theta. Okay, and we have to maximize this, but instead of maximizing this, we can minimize the negative of this, so it can be translated to this. let me again repeat myself. Instead of maximizing this, we can minimize the negative of this. So that is going to be the same, and then in this case it is going to generate a graph like this. Okay, so this was very basic explanation of this, because there is a lot of going on in the behind part of this, and you won't get a clear explanation of why we do not we shouldn't use MSE. But I am going to make another video for this specifically, and I'm going to explain this in that video, so don't worry about it. But for now, just be focused on this, that okay, why we do not use MSE, because it is not going to generate a convex function. It is not a convex function basically, and if you are not using a convex function, then you can stuck in a local minima, which is bad for our algorithm. Okay, so this was it for this video, and I hope that you understood the concepts here. So I'll see you next time. Thanks for watching.